All
All
right.
right. Can I just start?
Yeah, I think you
Okay.
should just start.
Yeah. All
We
right.
all know who you are.
Welcome, everyone, especially those of you for whom the local time zone is outside of normal working hours. Really appreciate you being here. Uh, so this morning we will do a review of common techniques and algorithms in online learning in MDPs. And I hope that this will start bringing together some of the things we learned yesterday, um, starting from basic planning, what is a value function, what are optimal policies, and then we also looked at some bandit techniques. Some of those techniques will make a reappearance in the two parts in this section on online learning in MDPs. My job in part one is to give you um, some exposure to online learning in a fixed MDP. So the MDP is not going to change as the learner interacts with MDP. And then my talk will be followed by Gergo's presentation, where he's going to talk about the changing MDP setting, which obviously is more challenging. And feel free to stop me. I purposefully kept the number of slides low, so please feel free to just stop me and ask questions. All right. So the outline is very simple. I'll sort of situate the UCRL2 algorithm, which is the main algorithm I'll focus on today. It is historically important. It started off a whole sort of series of papers analyzing regret in online MDPs. Um, uh, and so I'll focus on just one algorithm, give you pointers to other algorithms. I will go a little bit deeper into the analysis, like what is the main technique used to show the regret bound, and then end with some high-level discussion. Okay, so just to sort of situate this whole business of regret analysis MDPs within the sort of the RL world, as I see it, there are two strands of research that are directly responsible for for an algorithm like UCRL2. What does UCRL mean? It means upper confidence bounds applied to reinforcement learning. And the two stands for the version. There was an earlier version, UCRL, which required more assumptions. UCRL2 works under less stringent assumptions. So there's a strand of literature that connects to bandits, especially the UCB literature. And that's no coincidence, because one of the authors, in fact, there's a common author, Peter Auer, who also is an author on the UCB paper and on the UCRL2 paper. But the other strand is reinforcement learning itself, and this idea that maybe we want to analyze theoretically how well an agent is doing in one long interaction with an environment model as an MDP. So the use of the term reinforcement learning as a computer science technique, not in the sense of psychology, to the best of my knowledge, goes back to a very influential paper that Marvin Minsky wrote in 1961, titled Steps Toward Artificial Intelligence. And interestingly, apparently independently of Minsky, Waltz and Fu used the same term in the title of a paper that appeared in the control theory literature. And what is surprising is that 1970s was pretty much a very slow period for reinforcement learning. Not much happened, even though in 1960s, people were starting to get this idea that we can maybe create agents by using ideas from psychology, by trial and error learning using rewards. But 70s was kind of a dull period. And really, the field started to gather momentum in the 1980s. Temporal difference, all these famous methods that you hear about now were invented, and at least some basic analysis was done in that era. And then by the end of 1990s, there were enough results that the first edition of Sutton and Bartow came out, which is a very good introduction to the field of RL. It's actually not that technical, so I have regularly assigned it to undergraduates, and then they get a lot of value out of it, especially the early chapters. And there was an influential survey written in 1996 by Kelbling, Littman, and Moore. I was rereading it while preparing this tutorial, and I was very surprised to find the sentence. So I quote from that paper. They say, so they're discussing how to theoretically evaluate reinforcement learning algorithms. And they say, unfortunately, results concerning the regret of algorithms are quite hard to obtain. And that gave me a really nice feeling, because, within a span of about 10 years, sort of late 2010s, the first results on regret analysis in reinforcement learning started to come up. So a landmark result was, or a landmark algorithm was this algorithm called ECube, which I'll talk very briefly about, and another related algorithm called RMax. And then another milestone was Shyam Kakaday's thesis in 2003, this thesis was also mentioned in Mendy's talk yesterday. And then the focus of today's presentation is the UCRL2 paper. 3 authors, published in JMLR 2010. And it's really kicked off this area of sort of rigorous regret analysis in MDPs, using one long interaction with the MDP. So no resets, they'll be not in the episodic setting. And there was an earlier conference version in 2008. So that's kind of historically where we are situated, the paper that we are going to look at. And just a word about what do we mean by online learning, because online learning has slightly different meanings. It could be maybe you're designing online learning algorithms for just prediction, maybe you're in full information, we saw bandits. But today we are going to look at online learning, where an agent is interacting sequentially with a Markov decision process. And so the experience arrives bit by bit. You take an action, you see the state you went in, you see the reward. So slowly, maybe you build up your knowledge about the system. And in online learning, there is typically no difference there's no separation between an explicit learning phase where you can just do unbounded amounts of exploration and a separate evaluation phase where you will be evaluated. It may make sense in some applications. I'm not saying that that's not a useful separation, but in the setting I will talk about, that separation is not going to be there. So then there is a explore-exploit trade-off, which is obviously also there in bandits, but it's even more pronounced in some sense in the MDP setting. And this trade-off has to do with the fact that the agent is faced with this slightly contradictory goal of having to learn about the system and also taking good actions. Right? So maybe the tension is because maybe sometimes you have to take bad actions just to learn. Bad actions meaning actions that are not immediately rewarding. And so as one theoretical way to measure how good an agent is at resolving this trade-off, we might look at the regret. And again, regret is a very general notion. It has different instantiations in specific problems and in specific analysis frameworks, but it usually refers to a difference. It's a performance measure which is in the form of a difference. Difference between what? Difference between some yardstick, some comparator, some benchmark level of performance that maybe you can only achieve if you had full knowledge of the system. The difference between that performance and the agent's actual performance. How much reward did they actually get in, let's say, some fixed number of interactions with the system? And so this part deals with this explore-exploit trade-off as viewed through the lens of regret analysis in a fixed MDP. And then part 2 will look at the changing MDP case. See, there's a question. Oh, I guess someone already answered. And just before we delve into the algorithm and the analysis, just one word about the role of theory. We're in the Simons Institute for the Theory of Computing. It's a theory of RL semester. And I really feel that right now we probably at the start of another golden age of theory for RL, because there's so much applied empirical work that has happened, so many empirical successes. There's a lot of opportunity for theory. And I love this quote from this book, Computer-Age Statistical Inference, written by Brad Efron and Trevor Hasty, two of the most famous statisticians alive. And they say early in the book that if the inference algorithm race is a tortoise and hare affair, and by inference, just think, by inference, they really mean why algorithms work, right? So there are algorithms, and then there are reasons why they work. So let's call those reasons sort of inference, why algorithms work. So if the inference algorithm race is a tortoise and hare affair, then modern electronic computation has bred a bionic hare. So the hare is really running away much faster. The methods and the algorithms are just being developed at a breathtaking pace right now. Especially deep RL has really taken off in the last 5 to 6 years. And a quick search on Google Scholar, just looking at reinforcement learning in the title of papers, so that's an undercount. We see that there are over 16,000 papers in the last decade, compared to only 6,000 in the decade previous to that. And I think this is only going to increase. So 2020 to 2030, we'll see another maybe factor of 3 or 4, I don't know, hard to predict. And the field has grown. Sutton Barto's second edition, which came out 2018, is about twice as big. by the author's own estimation. The theory tortoise, because it moves more slowly, has lots of catch up. And I hope that this program can breed a faster tortoise, just like the electronic computation has bred a faster hare. Okay, so I want to lead into the UCRL2 algorithm, but I want to talk about very briefly two other landmark algorithms, ECubed and RMax, before I get to UCRL2. So I'm not going to go into the details of ECubed and RMax, just give you a very brief overview. So ECubed, the name comes from the three words explicit, explore, or exploit. That's why it's called ECubed. And it was a landmark paper because it kind of brought this view of looking at the sample complexity, looking for polynomial bounds coming from like theoretical computer science and especially Valiant's 1984 framework of pack learning. And it examined reinforcement learning from that perspective, that we want to give guarantees, theoretical guarantees that learning happens efficiently. And efficiently, hopefully, is both computationally efficient and sample efficient. And here, the part, as I will not go into the details, the only thing I want you to sort of know from this brief overview, if you don't already know ECube, then the one thing I want to point out is that this algorithm makes an explicit distinction between known states of the MDP and unknown states of the MDP, which of course, this distinction known and unknown changes over time as the learner visits more states in the MDP, the number of known states is going to increase. But it does maintain at every point in the algorithm's interaction with the environment, it maintains an explicit distinction between known states and unknown states. And if it visits an unknown state, and by the way, the distinction between unknown and unknown states is decided by the number of times you visited the state in the past. So if you land up in an unknown state, you just do what they call balanced wandering. So you just take the least right action. So you just explore. And you also maintain a partial model. Why is the model partial? Because it's only good on the set of known states. You have no idea what's going on outside of the set of known states. You don't have enough experience. So you have a partial model of the MDP. So it's a model-based method, but it only maintains a partial model. Maybe the model will never be a good model everywhere. It just depends on what happens. And the key sort of design principle in this algorithm is an explicit separation of exploration and exploitation. What does that mean? So at a high level, what it means is that the agent performs two calculations. Okay, so it says, well, given the partial model right now, is there a policy which will give me high returns, high rewards, based on that partial model alone? So that's the attempted exploitation. And also ask the question, is there a policy which will very quickly take me out of the set of known states? Okay, so maybe I can go and learn something about the unknown states. And then the key analysis technique is to show that it cannot be the case that both of these attempted steps fail. So one of attempted exploitation or exploration will succeed. And that's the famous explore-exploit lemma. And then there's also a simulation lemma which says that the value of the policy in the actual MDP restricted to the known states is actually close to what you think it is based on your partial model. So that's kind of the basic idea behind ECube. And so, as I said, it was landmark paper. This was followed by RMax, where RMax, the step forward was considerable simplification in the design of the algorithm, removal of this explicit distinction between known and unknown states. Sorry. It retained the distinction between known and unknown states, but it removed this explicit explore versus exploit design. So it used optimism in the face of uncertainty principle, which we saw yesterday. That it's a principle that says that if you're in an uncertain environment, you're making decisions, you have some uncertainty, maybe behave as if it's the best of all possible worlds. And in RMax, how it is instantiated is that in the unknown states, you just assume that they're fully rewarding. So if reward is in some scale 0 to Rmax, you just say I get a maximum reward Rmax in the unknown states. Often in theoretical RL, we normalize the reward so that they're in the interval 0 to 1. So then Rmax is just 1. Then you will just put a 1 in the states that are unknown. Okay, so this was another landmark because it achieved a simplification of the algorithm, and it also connected to this general design principle of optimism in the face of uncertainty. And what was interesting is that they analyzed not just MDPs, but actually stochastic games, two-player stochastic games. So they went a little bit beyond the MDP framework. Oh, there's some activity in the chat. Should I be? Oh, okay. That's just Java making a.
Yeah, never mind. It's just me.
Okay. No worries. I just thought maybe someone's asking a question on chat.
Okay, I tell you if there's a question.
Oh, thanks. Yeah, that would be nice. Okay, so just one slide on the general OFU principle. If you were not in the tutorial yesterday, then I want to make sure that everyone at least has some idea of what we mean by this OFU principle. As I already said, it's this idea that if you have some uncertainty about the true nature of the world, then maybe behave as if it's the best of all worlds that are somehow consistent with your experience so far. So that's the high level intuition behind the technique. And it has I think a long history. It definitely appears in that survey that I talked about, 1996 survey by Kelbling, Littman, and Moore, a section called ad hoc techniques. It just appears there because back then I believe there was not enough understanding of whether you could actually theoretically prove something about this type of principle. And the certain part of first edition also talks about that this optimistic. They talk about optimistic initialization. And they say it's a simple trick that can be quite effective on stationary problems. So there was this sense that maybe it's just a trick or an ad hoc technique. So it was nice that we could then later on come up with theoretical rigorous justification behind particular instantiations of the OFU principle. And it's also related to ideas in control. I'm no expert in control, but I at least know that there are papers on cost biased maximum likelihood estimation and something called the bet on the best principle, which is very much related to OFU. So just a summary of the introductory part of the talk. Now we'll get into the actual UCRL2 algorithm and its analysis. I want you to think of the evolution from ECube to RMax to UCRL2 as sort of elimination of explicit things in the algorithm. So ECube both had the explicit distinction between known and unknown states. It also had the explicit distinction between, oh, am I exploiting or am I attempting exploration or exploitation? And it didn't, in any explicit sense, embody the OFU principle. So that's the ECube row. Then RMax came along and said, well, let's keep this explicit distinction between known and unknown. Let's remove this explicit distinction between explore and exploit. Let's just, OFU principle will take care of that. We will just put our RMax on unknown states, and then the agent will naturally either explore or exploit. We don't have to worry about explicitly making the agent do that trade-off. And UCRL2 said, well, let's even eliminate this distinction between known and unknown states. It's anyways a little bit artificial to say that beyond a certain count, the state has become known. Maybe we just retain some soft notion of how uncertain a state is by just keeping track of counts, but we are not going to distinguish in this black and white way between known and unknown states. Okay. So what is the actual UCRL2 algorithm? The algorithm is going to run in episodes. And I want to make sure that there is no confusion on this point. You can use an episodic framework to analyze reinforcement algorithm where the episodic nature is built into the framework. So the episode maybe lasts some fixed number of steps. The agent interacts, and maybe then get resets to some initial state or initial state distribution. Here, our framework is not episodic. Our framework is that the agent is just interacting with the MDP, one long trajectory, no resets. So the framework is not episodic, but the algorithm is going to have its internal episodes. And what is the definition of an episode? In UCRL2, an episode is simply a duration of time where the algorithm is sticking to a fixed policy. Okay, so the algorithm design will involve episodes, even though the analysis framework doesn't have any episodic nature to it. And this trajectory, S1, A1, R1, S2, A2, R2, state, action, reward, triples, you see them. We will compute the regret at some finite length, capital T. We will work with a tabular MDP for now, with finite number of states, S, finite number of actions per state, A, and then the reward function R and P. So mostly standard notation. So hopefully that doesn't confuse anyone. And the high level description of the algorithm is as follows. Within any episode where you're going to stick to a single policy, you're not going to change the policy inside of an episode. So within an episode, use your collected statistics. What statistics? You create statistics out of the trajectory. You create these counts. How many times did I visit a particular state action pair? How many times it happened that when I visited SA, I transitioned to some fixed S prime? What are the counts? So these statistics, use these statistics to create a set of plausible MDPs, MDPs that don't seem to have been ruled out by the data I have so far seen. So that's a set of plausible MDPs. The true MDP may be somewhere in the set. Next step, find the most optimistic MDP in the set. Find the MDP where I get the maximum average reward. And I will define average reward soon, but find the most optimistic MDP, the best MDP that according to you within this set of MDPs. And then compute the optimal policy for this optimistic MDP, run it through this episode, and then have a certain criterion for when the episode ends. Okay, so that's the high-level description of the algorithm. So let's make things more concrete using some notation. So TK will be the start time of episode K. And I was talking about statistics, so let's give them some notation. NK S of A is the count for this particular state and action just prior to the start of episode K. Okay, so for all taus less than TK, how many times did I end up in this state in my history? Okay, this is N sub K is just before the start of episode K. So all the way from episode 1 through K minus 1, I sum them up and I put them in NK of SA. And also the counts for the triplets. So the transition from SA to S prime, I also maintain a counter for that. The third statistic I maintain is the reward, right? The total reward that I have gathered in a particular state action pair combination. And these statistics will give me estimates, point estimates. So right now I don't have a set. I have a particular single MDP, which is my estimate for what the true MDP might be. I can obviously divide the capital RK, the total sum of rewards, by the count. That's my estimate for how good this state is in terms of the immediate reward. And then I can also divide the triples by the count for the pair SA. And that's my maximum likelihood estimate for that entry, the S prime SA entry of the transition function. That's a point estimate. And at this point, an algorithm designer might say, well, I have an estimate. Let me just compute the optimal policy and follow it for a while. You can do that. That has names. It's sometimes called certainty equivalence in control. You just believe your point estimate, or the greedy strategy in CS. And the problem with that is you can get stuck in your own self-beliefs. So even in a simple problem like Bandit, if you just go with the point estimate, it's very easy to show that you can have linear regret, which is like the maximum regret you can ever get. So not a good idea to just believe the point estimate and do the optimal for that. In general, I mean, there might be more special structure which makes certainty equivalence look good, and certainly people do care about situations where you can prove that it's not such a bad idea to be greedy or have the certainty equivalence principle in picture, but in general, it's not a good idea. So we will create a set of plausible MDPs around our estimates. And this is maybe a strange looking definition. So my set of plausible MDPs, what is an MDP? I have already a fixed state and a fixed action space. There is no discounting here because I'm looking at one long continuous trajectory. So I will actually use average reward as my criteria for optimality. So there's no discount factor. State and action space are already fixed. So what is an MDP? It's just a reward function and a transition function. So to create a set of MDPs, I need to just create sets of reward functions and transition functions. How do I create them? Well, the reward function is any function RSA such that for all SNA, it's close enough to my point estimate. And similarly for the transition function. Where does the right hand side come from? Comes from concentration inequalities. Typically, with only NKSA visits to SA, you will not have high confidence at an accuracy more than 1 over square root n, right? So it directly comes out of standard, independent, standard like Hofdinger-Zuma type of concentration. And the log terms are there to handle the fact that you want these intervals to hold uniformly over time because you're going to take many union bounds over time and over state and action pairs. So there are logarithmic terms. And the delta will become obvious very soon. The delta will be the standard thing in probabilistic analysis of algorithms, where the algorithm will fail. Its theoretical guarantee will fail with some small probability delta. So obviously, if delta goes very small, then your confidence intervals have to become larger. And the last thing I want you to notice on this slide is an extra square root of s in the second inequality. And this is because we are using a very strong notion of locality around the point estimate for transition function. I'm using the L1 norm, which is so P of, this may be badly written. I shouldn't have written S prime here. I should have written a dot here. So I'm thinking of the transition function as a function of SA, which is, it's going to be a vector. And that vector has length S. And so I take the L1 norm between them, and that's why there's a square root S, because I have a very strong norm. I want this norm to be small, so I have to pay that square root S factor. Another way to see this presence of a square root S is that it's a very well-known equality, says that this L1 distance between two probability distributions, which is also called the total variation, can equivalently be thought of as the maximum disagreement between two probability distributions, maximum over all possible 2 to the power S sets. Right? So I have a distribution over S states. I can ask what is the probability for state 1, 13, and 17, some number. And I can take all possible sets and ask for what is the maximal disagreement between two probability vectors over all 2 to the S states. And that is, I think it's just a constant factor away from L1 distance. And so if you think about taking a union over all those 2 to the power S sets, then you naturally get a square root S. So the confidence interval for the transition functions is wider. Okay, so what is the actual optimism I'm going to do? Now I'm deviating a little bit for ease of exposition from the actual paper. The actual paper uses something called extended value iteration. They actually do everything efficiently, and Chaba's book is even more, I think the MDP chapter in the book Bandit Algorithms by Chaba and Tor, they're even more careful about proving that things are polynomial time. So they use linear programming. I'm going to be much more cavalier about this aspect of computational efficiency. I'll just assume that somehow over the set of plausible MDPs, you can find out the one which has the maximum optimal long-term reward. So rho star of M is in a given MDP M, it's the best average reward you can get. And I will define it in a later slide. But right now, just think of it intuitively as the best sort of long-term average reward that any policy can give you in the MDPM. And then conceptually, I'll search over all MDPs with finite diameter. And I will explain again, I'll explain what the diameter is. In the actual paper, they don't have this constraint of searching only over finite diameter MDPs. In fact, they show that once you do the extended value iteration, the diameter of the MDP you find will be not too big. But just for ease of exposition, let's say we are given a bound on the diameter of the 2 MDP. So I constrain my MDP space over the set of plausible MDPs that have small diameter. And within them, I choose the one which has maximum optimal reward. And tilde quantities will be optimistic quantities. So there is some true MDP M. I have a point estimate M hat at any given time. And then there's an M tilde computed at the start of every episode. So tilde quantities are optimistic, hats are estimates, and if you don't have any superscript, then that's just the true MDP. So I also have a pi tilde k, which is the optimal policy for this optimistic MDP M tilde. And then just follow this pi tilde k in this episode until what happens? Until some state action pair its count gets doubled. Okay, so Vk will be the notation for the count within this episode. And once Vk reaches Nk, which was the count just prior to the episode, I'll say, if it happens for any particular SA pair, I'll say, okay, episode over, start a new episode. And this doubling, this definition that involves doubling makes sure that the number of episodes will remain logarithmic in time. Okay, so Vk is the visitation count within an episode, and Nk is the count just prior to an episode. So obviously you have the recurrence relation that Nk plus 1 is Nk plus Vk. Okay, so I was talking about the long-term average reward, so I'll define it here. So if you have an MDP, and let's say you have a policy pi, which could even be non-stationary, even though with enough assumptions, you can show that a stationary policy can give you optimality. But suppose you have an M, a policy pi, and a starting state S. You can define the average reward simply as the lim sup of this average, right? So you sum up all the rewards in expectation that you get by running pi in M, starting from state S, take the expected expectation, so that becomes a number. You divide it by t, and you'll take the limit. You take the lim sup because how do you even know the limit exists? You maybe take this to take the lim sup. And an optimal policy will be one. So I'm jumping to the third bullet. An optimal policy will be one that maximizes rho m pi of s over all choices of pi. And actually, if you assume that the MDP has finite diameter, you can show that that policy will not depend on the initial state. So same policy can optimize the average reward from starting from any state. And that optimal average reward will be called rho star of m. So what is this condition involving a finite diameter that has all these nice implications about the optimal policy not having to depend on the initial state? Finite diameter is very intuitive. It just means that you can get from any state to any other state using some policy in finite time in expectations, right? So in a graph, what's the diameter? The diameter of a graph is over 2 nodes in the graph. So for any fixed 2 nodes, I'll find the shortest path. And then like, what's the longest shortest path as I arrange over all pairs of states? That's kind of how big my graph is. So very similar definition for MDPs. Take any 2 states, S and S prime, find the policy pi that transitions fastest from S to S prime. And by fastest, I mean takes the least amount of time in expectation to go from S to S prime. And that's the diameter, right? It doesn't depend on the reward function. It's solely a property of the transition function. So any questions here? So I think we are getting into notation heavy regime, and I just want to make sure that people are not already lost before I've started to analyze the algorithm. Chaba, are there any?
I did answer some questions just to get a sense, to give you a sense of what type of questions. One question, the very last question was about the computational complexity of finding an optimistic MDP. And I said it's high.
Yes, and especially the optimism is a big problem in even more complex problems like this. Even if you know how to compute the optimal behavior for a given system, it is a big ask to then say that do this over a set which may be weird due to the concentration.
There are some nice recent developments. Gerge also had a paper, and also Mark Abbey and Alessandro Lazaretti in the case of AQRs very surprisingly show that it's possible to do these things. So we shouldn't paint an overly black picture here. It's easy to overgeneralize of what we know and what we don't know. It's true that like straightforward analysis suggests that these problems are difficult, but sometimes you can use.
Sometimes you can exploit, like your cleverness in special structure. Like, but on the flip side, on the negative side, we do know that I think it's true in even linear in linear bandits that if you have a convex set of actions, then finding the best action is obviously easy if you have some kind of nice oracle access to the set. But doing the optimistic computation, I think there are such sets for which you can show as NP hard. So we know cases where there's a separation.
Yeah, but usually you can change the problem a little bit, relax things a little bit.
That's right.
And then the question is how much you're giving up on a regret. And then sometimes you don't actually give up on worst case regret. You just lose constant factors. Sometimes, it's a bit complicated, but it's even for the finite MDP case, we don't quite know what would be, the precise computational complexity of finding these optimistic MDPs with this L1 type of uncertainty, right? So we're not close to understanding this problem very well, even in finite case.
So I thought in your chapter, you actually show that it can be done in
that's the only thing, but like the computation complexity
beyond that, actual complexity.
To the power of, I don't know, like some big number, 26.
Yeah, right.
Oh, who knows? It's probably smaller, but it's still high.
Yeah, good question about the computation around the optimistic computation. There are still open questions. I think Chaba is right that we shouldn't necessarily paint a very negative picture, but it could be hard, and maybe you can get away from the hardness by relaxing.
Let me ask on behalf of the audience some of the questions. I'm not sure if I understand, but is diameter an upper bound on the distance? And if yes, how do we initialize this?
On the distance?
I think it's a distance in terms of like how many time steps you need to travel.
Oh, it is exactly that. TS prime is literally the sum of time steps that it will take for policy pi.
You can think about it as a distance.
It's also called the hitting time, I think, in Markov chains, like how much time it takes you to get to a certain state.
Yeah. And so that was the second part of the question. How do we initialize this? I think you should clarify here what the algorithm will really need to know about the diameter.
So in my version, so in the actual UCRL2 algorithm, you don't need to know much. You just need to know the state space and action space.
So here you are simplifying things by assuming that the diameter.
Assuming you know about, right? But that's not.
You don't need to know. Actually, you can show that if you remove that constraint, the algorithm is still fine, right?
Right. I just didn't want to prove that. Yeah, so I just used the fact.
Then like you have to use a separate argument that optimism only reduces the diameter. It is somewhat obvious though, right? Because the true MDP is in your set. It had some diameter. No, you have even more transitions, more things.
Right. How can the connectivity reduce? You can only get better connectivity.
Your travel time is going to reduce, right? So you can. Right. Okay. So can somebody clear up the definition of tilde MK? For me, it appears there's a typo in the definition on page 12 in the subscript of RMax. Okay.
Tilde MK is, you have a set of MDPs, and suppose you're doing this extra constraint of
I guess it should be a calligraphic set because there is.
Yeah, that's wrong. Yeah, that's just a typo. It should be a. So did I define my
set?
So the set is calligraphic.
Yeah.
And then you do the optimization over the calligraphic set. So this should be a calligraphic. Sorry, my bad.
Okay, I think we're on the same page. No more questions. Yeah, everyone's happy, I think.
Okay, let me stay optimistic.
Wait. One more question. Can you clarify again why you use the L1 distance for the transition?
It will become clear in the analysis. I'll point out why we need the L1 distance. We'll use a technical reason is we use a L1, L infinity inequality to bound a term, and that's where you need the L1 control.
Okay, good.
And that could be, and okay, I'll say something about extra factors in this algorithm. So I'll make some comments about L1. Okay, so we know what the algorithm does, and we now know what the diameter is, and that makes sure that you have a well-defined optimal average reward. The last technical piece of machinery I need before we can start analyzing the algorithm. I have what, 20 more minutes? Is that right? Okay, good. So the average reward Bellman equation. These are slightly different from the discounted case. And they also have less uniqueness. So everything is somehow more subtle with average reward. But here they are. And again, if you have finite diameter, then existence and everything is taken care of. You have solutions. The optimal policy is going to satisfy an equation like this. The number rho star plus a function h star of s will equal the reward, the immediate reward that you get in S by when you do pi star in S, plus sort of the usual thing, right? The average of under the next state distribution of the same function that you have on the left-hand side. Unfortunately, to introduce more complications, this bias vector, which is kind of the analog of value function, is not unique in the average reward case. And you can see this in this equation already. I can add a constant to every element of h star, and because I hit it with the probability, it's just going to give me that constant on the right-hand side, and I get the same constant on the left-hand side. So it can, all entries of h star can shift by a constant, and it's still a solution. In fact, it's even less unique than that. So h star is not unique, but certainly it exists, there is one H star that will satisfy this Bellman equation, and we will use this Bellman equation in the analysis. The second technical information I need is the span of H star. What is the span of H star? It's simply the range, the minimum to maximum. The span of H star, it's very easy. It's not that difficult to show that it's actually upper bounded by the diameter. And so if you have some kind of convention to normalize these bias vectors, maybe the minimum entry, you will always normalize them to 0 because you have this freedom of shifting them. If you normalize them, let's say the minimum value to 0, then the infinity norm and the span are the same. Okay, and we will use this fact. We will bound the infinity norm of H star by the diameter. Okay, so now begins the sort of regret analysis. What is going to be the regret? It's the difference between T star times the optimal reward. So if you know the MDP, you can compute rho star M, and you just multiply by T. That's a very good yardstick to shoot for. And you will subtract your accumulated rewards from that yardstick to say, that's my regret. And it's a function of the MDP you're in. It's the function of the algorithm script A that you're using. It also depends on where, potentially could depend on where you start from and the total time horizon. And the main theorem in the UCRL2 paper is that with high probability, regret is bounded for any starting state S and any T, and for any MDP that has a finite diameter by ds outside the square root and then inside the square root AT with some log terms. Okay, so you get a linear dependence in state space, a square root dependence on action, square root on T, and linear dependence on diameter. Okay, so now I'll see how much of the analysis I can go through. Let me actually at least give you the basic idea, and then I might have to transition over to the discussion section because I am running out of time. So how do we analyze this algorithm? The nice thing is the algorithm doesn't change the policy within an episode. So you can decompose this business of this task of controlling the regret to controlling the per episode regret. What is the per episode regret? The per episode regret is just it's just a regret in that episode. So it's this term over here, the counts to different states and actions during that episode. Remember that was week A. That times the sort of the difference between the optimal average reward and the reward you get in that state. That's how much regret you incur in episode K. And the total regret is just a sum of these regrets. And I already told you that because of the doubling criterion, it's fairly easy to show that there are not going to be more episodes than SA and then log of T to base 2 or to any base, since we're only looking at things without precise constants. The actual bound actually has a precise constant, so it's not order. You can actually get an actual constant, it's 34. But I'm not going to keep track of constants in my presentation. So once you look at per episode regret, the first thing you do is you first show that you are actually optimistic, that the concentration that you're using actually ensures that the MDP, true MDP will lie. It's not going to escape out of your set with very high probability, right? So standard concentration tells you that at any given time, if you constructed a confidence set, the probability of the true MDP not being in it is minuscule, right? Delta over some high power of T, and then using union bounds and stuff like that. It's technical work, but conceptually there's not much going on. You can very easily show that the contribution of the regret because of the failure of the confidence interval is not more than square root T, and it doesn't even give you all these extra factors of S, A, and B. So that's not the dominant term. What's the dominant term? The dominant term is, well, assume that your confidence regions were correct. What's the regret you incur in that case? Okay, so if my confidence intervals are correct, this possibly is conceptually the heart of the analysis, even though technically a lot has to come. But conceptually, I feel like this is the heart. So you look at the per episode regret, there's a rho star. The agent has no idea what rho star is. But because it's using optimism, and because we know that the true MDP is in the set, rho tilde k, which it can compute, is obviously an upper bound. So I can replace rho star It's multiplying a positive quantity, so I'm not cheating. I can replace it with an upper bound. And so I get this upper bound on the regret. And interestingly, everything here is computable by the agent. The regret is not computable because the agent doesn't know what rho star is. But this upper bound that we will analyze is actually computable by the agent. So we will work with this upper bound where rho star has been replaced by rho tilde, which is this optimistic, which is the optimal reward in this optimistic MDP. And also recall the Bellman equation for rho tilde. Bellman equation says that now I have written it in vector matrix notation. So rho tilde times a vector of ones plus the bias vector for this policy H tilde is equal to R tilde K plus the transition, this fake transition kernel P tilde K. It's the fake transition kernel because it doesn't correspond to what actually happens. It's the transition kernel in P tilde that corresponds to pi tilde. It's a fictitious quantity. It doesn't exist in the real problem. But this equation will be satisfied. Okay, so our job will be to just massage this expression before we can start to see elements of this equation in the regret. So what do? You first of all add and subtract an R tilde. So you had rho tilde minus R. You add and subtract R tilde. Why do you do that? Well, because you know that R tilde and R are close. They're close because that's how you generated the set. So this term doesn't actually create a lot of trouble. Or in other words, it can be handled by terms that are strictly smaller than what this term contributes. So the dominant contribution to the regret comes from this visitation count weighted difference between rho tilde and R tilde. And this is actually nice because I can use my Bellman equations. So I know that the Bellman equation holds, and I have a difference between rho tilde and R tilde. That's kind of interesting because the difference between rho tilde and R tilde can be transformed into using the Bellman equation between, I can replace rho tilde times 1 minus R tilde with simply P tilde times H tilde K minus H tilde K. So just move this R tilde over to the left-hand side, H tilde to the right-hand side, and that explains the last step here. Okay, so in some sense, it's very nice. Like once you do this optimistic thing that you replace rho star by rho tilde, the rest of it is extremely natural. It's almost like what you might try, given the fact that you have to use the Bellman equation somewhere. So it follows very naturally. And now we are left, now the dominant term in the analysis is this type of term where the visitation counts. We're taking inner product of that with P tilde H minus H tilde, which can be factorized as P tilde K minus identity times H tilde. And recall that P tilde is a fictitious transition kernel. It's the transition kernel of pi tilde in a fictitious MDP. But pi tilde has a real transition kernel in the real MDP. So let's call that P. And this is the last step in the analysis. Then it is just calculations. So once we have arrived at the difference, looking at the difference between P tilde and I, you just say I'm going to add and subtract PK, which is the transition kernel of pi tilde, your optimistic policy, in the true MDP, which you don't know, but we are doing the analysis, so that's okay. We can use it in the analysis. The algorithm never uses PK. It cannot, it doesn't know it. So we add and subtract PK. And what's interesting is that you can sort of start to see why both of these terms will be easily not so hard, like won't be that hard to control. The term involving P tilde K and P, that's very similar to the term involving R tilde and R. That's going to be small because you have some control on how big the optimistic set is. You have some control on how big P tilde and P tilde minus PK can be. So that control will come from your construction of the plausible set of plausible MDPs. A little bit of intuition about the second term here. We have the visitation counts in episode K hitting PK minus R. What is PK minus R? PK here is the transition kernel of pi tilde K. If pi tilde K achieved stationarity, at stationarity, there would be a stationary distribution mu sub K such that PK mu K would just be mu K. That's the definition of stationarity. Here, I'm not at stationarity. I just have some counts, but it's going to be small because it's like a random fluctuation beyond this. This term would actually be 0 if Vk was replaced by the stationary distribution of pi tilde K. But we're not at stationarity. So we get a martingale difference sequence plus another diameter contribution each time the episode changes. But again, this does not give you the dominant term. The dominant term still remains the first term, which is about controlling P tilde and P. Because I have only 7 minutes left, I will spare you the details of the math beyond this. So conceptually, I think the proof finishes here. You still have to do algebra and calculus and control of some finite differences to control this term over all episodes. One thing to answer a question about why L1 norm, that's because of this dominant term. So when you analyze this dominant term, you get a term where the difference between P tilde and Pk hits H tilde k. What do we know about H tilde k? It has a small span. Why? Because the diameter is small. And it's the infinity norm of H tilde k, which is controlled by the diameter. So I can only put an infinity norm here, which forces me to put an L1 norm on the difference between probability distributions. And that's where that's the source of L1. At least if you do this analysis. I'm not saying that there's no other way to do the analysis, but this analysis, that's the root of why the L1 norm appears. Okay, so I don't think there's anything else conceptual I want to say here. This diameter that you get from the infinity term just comes out. 1 square root s directly comes from the right-hand side of the P tilde concentration. That's one source of S tilde. And then you get a term involving the visitation counts that are normalized by the previous visitation counts, which gives you another square root SAT. Okay, so D square root S times another square root SAT, and that's kind of you can at least start to see where the different contributions in the regret are coming from. And I'll skip this slide. Why the count term gives you a square root SAT. And the obvious question that you might have at this point is, well, we did a lot of bounding. Some of it might be loose. We're using L1, L infinity. God knows how many upper bounds we've accumulated, how much we're paying. So is this optimal? Is there any hope to show a lower bound? In fact, the paper does show a lower bound, and a pretty strong lower bound. It says that for any algorithm, on any MDP of non-trivial size, so more than 10 states and actions, and diameter which is large, which is very reasonable, log A of S, you can show that the diameter has to be at least like 3 log A over S or something. So this is not a stringent condition at all. And for any T which is sort of large enough, the regret is going to be at least square root of DSAT. Okay, so at least the upper bound is capturing all the main sources here, the diameter, the state space, action space, and time. But of course, if you notice that there is a discrepancy here, the upper bound had D and S outside the square root, while the lower bound has them inside the square root. So what is the optimal? Can we match the lower bound and upper bound? The original paper left this open, but recently there's an archive preprint which I haven't verified myself, so I can't say with full confidence that it has managed to remove the gap. It's not published yet; it's just a preprint. But the claim is that it's the lower bound that's tight. So the upper bound can be improved, and the D and the square root S. And I think the idea is that one factor of square root D you can avoid by just using more interesting concentration inequalities. So if you're using the most naive concentration inequalities, you can use things like Bernstein. That will give you one source of improvement. And I think also this L1 norm business, I think the paper does a different node construction of optimistic MDPs. But what's interesting is that the overall it is still UCRL. So they call their algorithm UCRLB and pending checks. And I think this will be a good reading material for a reading group. You could spend some time looking at this proof to see how the gap is eliminated. So in the 3 minutes that I have, I will not say anything about Thompson sampling, except that in Thompson sampling, instead of creating a plausible set, you work with the posterior, which means that you have to have a prior. You look at the data, you get a posterior over MDPs. You draw an MDP from that posterior, and you just compute the optimal policy. So you don't have this optimism inbuilt. You might still have some probabilistic optimism because maybe there's some probability that you will be optimistic, but posterior sampling has been taken outside of its bandit origins. Actually, very old algorithm going back to 1933, and we have tools to analyze posterior sampling, but I don't have time right now to go into the analysis. What has happened since UCRL2? It's 10 years ago, so a lot has happened. Other algorithmic ideas, including Thompson sampling, injecting random noise. Random noise could be injected into the trajectory. Maybe you randomly perturb the trajectory. You could perturb value functions. So this idea that maybe we don't need full-blown optimism, maybe we can just add some randomness and hope that that will inject enough probabilistic optimism so that I can still prove regret bounds. That those algorithmic ideas are definitely in the air, and there are papers on some of these already, but more remains to be done. You can also look at I was looking at average reward, which makes sense if you have one long trajectory, but certainly you can look at episodic problems where there are resets. There's work on episodic setting as well. All the algorithms I talked about today, ECube, RMax, and UCRL are model-based because they explicitly maintain a model. You might ask what happens if you have model-free algorithm. That has also been studied. And large state spaces, whether you talk about factored MDPs or functional approximation, and then within functional approximation, as Chaba mentioned recently, there's been a lot of work on the linear MDP case. And you can prove regret bounds in that scenario and just infer the tabular case as a special case where the dimensionality is just S times A. So that has happened, and this is also coming to the edge of the frontier of knowledge. There's a lot of these issues are still being addressed. Some other issues that I'm quite interested in are aspects related to transfer and curriculum learning, learning on one task, using that knowledge on another task, choosing maybe tasks. The agent itself can choose the order of the task, or maybe it's given to the agent. All of those, how to analyze those situations theoretically, I think is a fascinating open area. Also causality, can be used some type of causal modeling, and can it help with, especially with transfer, because there's this intuition that maybe causality has to do with things that are invariant under various perturbations of the system. So if you can learn something common across a lot of tasks and encode that commonality in some causal way, maybe you can enable transfer learning in RL and analyze it theoretically. I assume that states are perfectly observed. You can have, obviously, in most real problems, you'll have partial observability. There are some papers dealing with it. The computational problem just goes up because even if, as Chaba mentioned yesterday, even if you know the system, I don't know if it was Chaba or Mengi, but one of them said that these p-space hardness results for computing optimal policies for MDPs. But maybe you define regret with respect to a less burdensome competitor. You can say my competitor also is bounded computationally, and I just want regret against a computationally bounded competitor. And then finally, multi-agent RL, where you don't have a single agent, but you have multiple agents. What does regret even mean? Are we trying to converge to some equilibria? So there are many interesting questions around multi-agent learning. I did go over a little bit, but I'm happy to stop here. The summary is stating the obvious. You can read it. And my slides will be available. I already posted them on Discord, and all the references in part of the talk are at the end. Thank you.
Yeah, thanks, Ambuj. Cheryl and real clap. Yeah, in the meanwhile, I try to answer the other questions. I think that some people were just wondering about this optimism and why, like, again, an intuitive understanding of why optimism does help. Right.
Question about what stops us from getting stuck.
Always following one policy and therefore not exploring. Well, you switched to new policy, right? Okay, I guess, like, so Bora was asking this sequence of questions which tries to poke at like how optimism helps, like why not use the point estimates and so on and so forth. So I was just saying that I would just think about what happens in bandits, but maybe that example could be explained a little bit more. I couldn't type up, like a detailed answer. So maybe you could just like say a few words about why does it happen that if you're in a bandit is a special case of MDP. So if you are traveling bandits,
right. So just believing your point estimate, it's very easy to show it's bad, even in a bandit, even with just 2 actions, which is kind of the least sort of interesting case. If it's just 1 action, then anything you do is optimal.
Okay.
So even with 2 actions, you have an action which is better, an action which is worse according to its true mean. But these are not deterministic, right? So there is some randomness. Maybe the first time you try both of them, the better one gives you a sample which is lower, right? So you think that, oh, the better one is lower. So, okay, so I'm going to just go with the other one. That arm's estimate will get continuously refined, but it will remain above your poor estimate based on one sample of the other arm. You'll be forever stuck in this false belief. Yeah. And the problem is you put in too much trust in that one sample from the better arm. You thought that it was wrong. You will never come out.
Optimism fixes this?
Optimism, because eventually the width of the worst arm is going to shrink, but the width of the big arm is not shrinking. So at some point, the upper confidence bound will still be up. So you will be forced to try the other one, and then hopefully you will not, with high probability, the random samples do give you a good idea.
And so the same reasoning works in MDPs as well, in a nutshell? Somehow?
I think so. I think in a nutshell, it's kind of the issue is actually in MDPs, if you look at LQR systems, I think there's a very nice geometry of what is the manifold. There's actually a very nice geometry in LQ systems. In MDPs, there's no geometry, it's all discrete. But in LQ systems, there's a geometry. You can start understanding what is the manifold of sort of systems where you get trapped in this false belief. Mm-hmm. So you have a system, you have a controller. The controller and the system produces, it's just a Markov process. That's the process that will give you information if you don't change the policy. And you can say that, well, based on the information that I get, what systems will kind of be indistinguishable? And if there is a gap in sort of optimal rewards between those systems, like you don't have any information to distinguish between them. So the bet on the best principle paper by Bitanti and Campi that I have referred to, they have a nice discussion about how optimism allows you to escape this sort of, you get stuck in this fixed point where you get data, but that data is from your own sort of falsely believed estimate, and you get stuck in circular reasoning almost. And optimism, and they have a very nice discussion of how optimism allows you to escape from that vicious loop of belief.
Mm-hmm. Okay, so there is another question from Sebastian de Petier. He says, so as far as I understand, the transition function and reward function treated as statistically independent by UCRL2, maybe no noise, right, in them is treated as statistically independent. Maybe that's what is meant, statistically independent. What if there is some known dependence between the two, so that, for example, observed rewards are also informative toward the transition function? I imagine we should be able to do better in such setting. Is there any work in the setting that you know of?
Oh, I think I understand that. Yeah, okay. So I think by statistical independence, you just mean that I'm allowing all the reward, like I'm taking a Cartesian product of sort of allowed rewards and allowed transitions.
Yeah, it's like condition on where you are, the noise in the reward and the noise in the transition could be dependent or could be independent. And the analysis doesn't really care about if they are dependent or independent, and whether there is any room for improvement if there was some dependence. But I guess, go ahead. I don't know, like I have some thoughts.
Yeah, my preliminary feeling about this question is, but first of all, I don't know of an actual paper that would answer your question. But my guess right now is the principle still applies. Your estimation will become more complicated. So you will have to estimate P and R jointly. Maybe
it becomes worse, right? Like if you have dependencies, then you sort of have less information. Like it's like flipping two coins or flipping one coin. Like you're interested in the means, and
Right. If you the more independence you have, the more effective sampling.
Yeah, that's my gut feeling. But if you had dependence, you would need to apply an extra union bound, and the analysis would go through. So it's like a log 2 or something like that would be lost, I think.
Yeah, shouldn't be a big issue. I feel like that's what I
mean. But I think that there is an underlying different question which is related, which is the structured MDP setting, where maybe, you know, like you see a reward of 0.7592 at this state action pair, and from that know that this was your MDP. And then, you know, like there could be some structured MDP setting, and that's interesting. And how to go about that. Are there any papers that you have seen about this?
I mean, structure. I have seen papers on, like, there's analysis of optimism based and Thompson sampling in the factored case. But I don't think that gets to exactly what you're saying. But that's
So I think that there is one paper I can think about. Maybe we can post the pointer later.
Yeah, actually, we can use Discord. I'm trying to build a bibliography of sort of interesting variants of basic regret analysis, and I think Discord is a good way to collectively use the crowd's wisdom to.
Okay, so we have plenty of questions. I'm happy to stay. If people need to leave, they can leave. But,
yeah, I think officially we are done. So if people need
we are officially done. If you need to, you know, get some exercise or fresh air or whatnot. But I'm happy to go.
There's also a gathered town, I think.
So yeah, Gather Town. But I think that for answering the questions, this is actually a little bit better than Gather Town. In Gather Town, like,
that's true.
I don't know, like it would take time to get together, and like we would lose the questions. Okay, so Esma says, could you please introduce any paper with theoretical results that uses transfer learning with online RL?
So I think doesn't Mendy have a recent paper on? Might be multitask, not transfer, but I think she has something.
Yeah,
I remember.
Chab,
I am not even sure if maybe you were on it, because I just can't keep track.
No, but
if I find this, I think the answer is yes, and once I have the precise reference, I'll post it on Discord. Let me make.
Yeah, I think we should just post. I know about a few papers. I think maybe Emma does have a paper.
Emma might, yeah. Emma, are you still here? She was here a few minutes ago.
Sandra is a long time player in transfer learning, online RL, and I think that they do have.
Oh yeah, Emma and Li Hong Li had a paper on like sample complexity issues, right? Yeah. There are papers for sure. We just need some time to dig them up.
Yeah, and if you guys can ask these questions in Discord as well, like everyone, and we'll be there and we try to answer. How to understand the stopping criterion of episodes, and I would add to that. So this Chen's question, I would add to that how important it is to use these episodes and this stopping criterion. Are there other ways to cut the episodes? What if we don't have episodes?
Yeah, so there is an exercise actually in Chaba's chapter that shows that if you don't have like if you just keep changing it each time, then that's not a good idea. So you definitely need to wait and let the policy run for a while. So that's one part of what I wanted to say. The other part is, well, how important is it to do it precisely in this way of like you wait till some state action doubles? I don't think it's that important to do it in precisely that way. There are I think plenty other strategies for episodes. Some of them even like you can just, if you know the time horizon in advance, I think you can do something fairly simple to change the episode. So I wouldn't say that doubling is somehow a crucial piece. I think the crucial piece is the construction of the optimistic MDPs, doing the optimism, and then sticking for the policy for a while. Like you certainly don't want to recompute each time. I think that's the sense. The rest is, I think you could argue that other choices could have been made and have been made. Actually, for posterior sampling, one of the problems with this with this definition of episode changes is that a crucial step in the Bayesian regret analysis of downsampling gets stuck because your episode length is not measurable with respect to the history you had at the start of the episode. So the solution of the problem was to redefine the episode changing rule so that you actually get measurability. And there were some incorrect statements made that you just do the Bayesian regret analysis, and then I think Ben Van Roy had an archive preprint about why it's not so obvious. It's a subtlety, and so yes, this episode changing business you have some flexibility, and in fact, that flexibility has been exploited to prove Bayesian regret of Thompson sampling in this infinite trajectory business. Chaba, would you qualify that?
Yeah. It's good. Oh, okay.
You should have come up earlier. Why do some people prefer frequentist regret analysis? Chaba, you want to take that first because you have maybe have a more longer term perspective on things.
Well, I think so. The Bayesian regret analysis. So to me, the fewer assumptions you're making about the problem you're solving, the stronger the result is.
Mm-hmm.
In a sense, there is a clear advantage to the frequentist regret analysis. And I think that that's probably the answer that most people who care about frequentist regret analysis would give you. The only question is, why are there people who don't care about the frequentist regret analysis to me?
Oh, so you're flipping the question.
I'm totally positive about, like, I really do care about, like removing assumptions, and how far you can push this. And in this sense, like Bayesian regret analysis stops a little bit earlier. And then what's miraculous though, is that a lot of times the algorithms designed for the Bayesian case still survive, maybe with some little modifications. Sometimes you actually do have to modify them to get reasonable regret. So there is some recent paper that shows this for linear bandits and Thompson sampling. But okay, so I would flip this question.
I would flip too. Yeah, I think you're talking to people who inherently are frequentists. So I'm the same as Chaba that. Yeah, I want bounds that I know just hold. Like in Bayesian regret, you're saying an average over some Dirichlet prior. Like, how do we know? Maybe those MDPs are too simple.
Being a good scientist means that you're agnostic as much as you can, and you only make assumptions when you have reasons to believe, and assumptions that are just convenient are not a good reason to hold those beliefs.
There's a question about reductions. So do we know of reductions Bayesian to frequentist? I think you can make a very simple conclusion, which I think Ben Van Roy, one of his paper, has it, which if you know that expectation of regret is less, you can apply a Markov or something and say that there is a large probability set on which the frequentist regret is bounded. So you can do something very simple like that. I don't know of reductions. I'll just echo what Chaba was saying before, is that it's often the case, and I don't know, is there a deeper reason, but it's often the case that you design a Bayesian algorithm and which you can actually analyze it using frequentist analysis. And surprisingly, confidence intervals again show up, but only in the analysis, not in the algorithm itself. Obviously.
By the way, I don't like that when that shows up. If you try to analyze expected regret in a Bayesian setting, I think you are butchering the problem if you bring in confidence or concentration-based bounds.
No, but if you want a frequentist bound for a Bayesian algorithm.
Oh yeah, okay, yeah. But
then
like even for the Bayesian analysis.
Oh yeah, for the Bayesian analysis, no, yeah.
You turn to basically doing some part of the frequentist analysis, which is less than ideal. I understand why
less than ideal, yeah.
Do it, or I've done it too. But if there is a way to avoid it, then maybe you can get tighter bounds. Okay, so there is a question. It just appeared it is always better to turn a PAM-DP problem into MDP for problems that can be turned into MDPs if enough observations are stacked together. For example, when the actual state is too large is there a trade-off in terms of convergence rate? I think this relates to the question of that in these analyses, we assume that the states are observed and there like a minimal representation of the state is observed. Like you can imagine many other things. You can imagine that you are clumping together a few past observations in the video game, and then you have this overblown representation of the state, hoping that like, okay, that's a state representation that is a valid state. But it may not be a state, that's the first problem, or if it's a state, it's an overblown representation. So what do you say for people who worry about these things?
You're asking me about games. I don't think I'll have much to say.
I think actually has somewhere I can tease around at least answering partly parts of this question. It's an active area of research trying to understand.
One paper where something like this is happening theoretically is a paper actually by Ronald Ortner on restless bandits, where it is a POMDP, but they convert it into an MDP, but they actually truncate, the state space becomes countably infinite, so they have to truncate it. And I've often worried about in that special case of restless bandits, if there is some optimal truncation. And I think that's related to the question here, because the question here is, I could just keep my POMDP and apply POMDP regret bounds, or I could enlarge the state space and apply MDP regret bounds. How do I compare these two? And is there as was asked, is there a trade-off between convergence results? I think the question is very interesting. As Chaba said, I think we are still trying to understand some of these issues. Last question. Oh, no, not last, but Ibrahim Jamal El Shar is asking,
Lots of questions.
What's that?
Do we know reductions from Bayesian to frequentist regret?
I think I already discussed that.
Yeah. Okay. For Thompson sampling, every time sample from our posterior, we saw some, can we make use of them by having a prior on policies that we can update the prior from the optimal policy of the sample MDP and then sample policy that we used to act on the episode from our prior on policies.
So here, I guess the desire is to not keep a posterior at the level of models, but just keep it at the level of policies. Is that the question?
Yeah.
This is pretty much, I think. I think for value functions, certainly there's work of that flavor, where you don't want to do like Thompson sampling, or, well, I don't think you can actually call something that only operates at the level of value functions or policies some Thompson sampling technically, because you don't have the full parameter space somehow. But Thompson sampling type algorithms definitely exist, where you add randomness or posterior type objects at the level of value functions. For policies, I'm not sure actually. I don't know if there's a paper that says there are expert type algorithms like polytech type business, where you maintain some weighted distribution over policies.
Yeah.
But it's hard to say that that's posterior.
You know, like putting distributions over value functions that used to be a core topic in Bayesian RL. It's not too active these days. Other papers where UCRL type of algorithms are used, but instead of looking at regret, we are more interested in finite time analysis, like how close the the value function of the current policy is to optimal.
Oh yes, by no means is regret analysis the only theoretical.
Yeah, so this is more like you don't care about like exploration cost, pure exploration problem in MDPs.
Yeah, again, I think there's a line of work. The one that's come to my mind right now is Emily Kaufman has a recent paper on pure exploration.
There is a bunch, like at least 3 groups working on.
Yeah, and you can look off references of that. So there is definitely work. I don't want. Maybe I should have pointed this out, that regret is just what I focused on, but it's by no means the only.
It's a very reasonable one. If you're online, most of the time you would care about regret, but maybe sometimes
Right.
You're given a free pass for a while, and then after that there is no learning. I
Yeah.
find that not too natural, but maybe external circumstances are such that you really have to do that. Um,
Oh, there's somebody's trying to make an analogy between simplex and ellipsoid on one hand and frequentist and Bayesian. I don't see the analogy. What is the analogy? The tension between frequentist and Bayesian regret is, I don't think it's the same tension as. I mean, there is some commonality because simplex is exponential in the worst case, but its smooth complexity is polynomial. So I kind of see what this question is getting at, but I can't make it precise. I think the analogy isn't quite.
Yeah.
You could, and actually, Chaba, I wanted to pick your brains about this. Is that we have worst case, so what we call frequentist analysis of give me a bound for all MDPs. We have Bayesian, which is averaged over some prior. There is smooth analysis in theoretical computer science, right? Which is between average case and worst case, where you say that I'll take the worst case, I'll add a perturbation around the worst case, and I'll look for polynomial bounds in the amount of perturbation and the relevant quantities. Do you think there is any role for a smooth analysis type of framework that sits somewhere between worst case and expected?
I don't see of gaining much from doing this in the settings that people typically look at. I think in theoretical computer science, you do this to show that the adversary who chooses the worst case instance is kind of weak. Because if you add a little bit of noise, then its power is quickly dropping. I think the adversaries here are kind of noisy already. And they have a lot of power because of noise. And if you add more noise, it's not going to make the learner's job easier, right? So the worst case is not like, it's not that bad. The worst case is not that bad in our case. It's just information theoretical worst case thing.
No, but hold on. It's not bad, let's say, for UCRL2. But we talk about, and smooth analysis has shown up in this greedy. So we were just talking about, greedy is bad because in the worst case it's bad, right?
Yeah.
But maybe if you did a smooth analysis of greedy,
okay, sure. You could change the models that way. Yeah. Then some model could be, okay. So again, back to the simplex analysis, that the smooth analysis of simplex shows that simplex is not actually that bad.
Right.
Sure. I think that people do smooth analysis in an effort to understand why certain algorithms behave the way they behave in practice, like surprisingly well. When the worst case analysis shows that they shouldn't be very good, at least in the worst case, and that's an attempt to explain that. And yeah, in this regard, I know of papers, for example, it's not really smooth. Oh, I think that some people did analysis of greedy algorithm in linear bandit setting with smooth analysis.
Yes, that's the paper I'm referring to. Yeah, because then you can show that greedy is not that bad because of, and you can kind of see, right? Like the gap, if I randomly perturb the means, then obviously there will be some gap. So maybe the case where greedy really fails is like some tiny region in the space of all problems. So
I don't believe in that, because if you just think about the finite term bandit case, how the greedy algorithm fails in that case, it just
in the finite, no, yeah, I think, but that paper is in the linear contextual case.
Yeah, and then I think that there are other reasons to believe that the linear contextual case may not be that bad, because, for example, you could have benign context distributions or whatnot. And I would rather try to understand what are these benign settings than, artificially add some noise and like analyze.
And so you get exploration for free in some sense.
Yes, there are some benign cases. And then design an algorithm that is adaptive to that,
Right.
and like turns down exploration when you don't need exploration, and turns up exploration when you need exploration, rather than just saying that, oh no, greedy is good overall, because like this analysis shows that if we add sufficient amount of noise, then it's not that bad. That seems to be a bit weaker than what you can do. I think that we are not in such a dire situation where we would need to do this.
Yeah.
Maybe one day.
Yeah. I think you're right. I think the smooth analysis was trying to grapple with a decades-long question of why is the simplex in practice so good? If we had that type of situation in RL where we had an algorithm which was amazing, but its theoretical bounds were exponential, then we would maybe worry about it.
Yeah.
Gentlemen, I'm sorry to interrupt. Can I have Gary?
Oh, it's 1:28.